So feel free to start with your questions. I just wrote some keywords. Maybe surely I'm missing maybe a lot more, but just for you to maybe recall if there are any questions.
What is about singularities?
That's one Alex has presented in the last 10 minutes.
No, I mean above. It's QFT what?
Non-locality.
Non-locality.
So it's non-locality, infinite derivatives, QFT non-locality again?
Yeah, QFT.
Okay.
Well, there are QFT non-locality. One is infinite derivative non-locality and the non-locality is in QFT. So that's what I mean. Yeah. I think I'll see you right now.
Yeah, okay.
Yeah.
Just an extremely naive question for Alexei about the last thing you said. So I just want to understand what is in general the expectation, and it's something I don't work on. So it's not that I have an idea. So is the expectation that if I think of gravity as an effective field theory and I have my infinite tower of higher derivative corrections, that the higher derivative corrections themselves will tell us about desingularization of black holes? Is that an expectation to have in general or not?
Yes, expectation. Yes, expectation is that higher derivatives. Well, first of all, we are trying to claim that these higher derivatives will make it not rather effective field theory, but some solid renormalizable unitary model. Okay. But apart from this, yes, there is expectation that these higher derivatives will remove what we now see as singularity in some configurations in GR or finite higher derivative gravity.
As a general statement, that's
Yes. Yes. In general expectation. Let's put it like this.
Sorry.
All right.
Yeah.
Yeah.
Is it a follow-up question?
Mine is a small follow-up.
Okay, please.
I think it's more for.
I just wanted to know if these non-singular black holes have horizons generically. No. I mean, other geometry. Do they have horizons?
Yes, they can have horizon. Okay. If you want, I can draw you just a simple plot. Yeah? Expectation is to have like this. This is your Schwarzschild, and this is what we do now. Okay, this one. This is R. Okay, and these are your two horizons. It is a function which is in front of this, and here some regulator. Okay, this is what we did, and then we say that this depends on alpha, and when alpha goes to 0, things become weird in infinite derivative case.
It's a short follow-up. So, sorry.
Okay.
What do you say about Big Bang singularity?
First of all, I didn't say anything about Big Bang singularity, okay? But expectation is the same. Singularities will get resolved. Actually, you remember it was said once by Edward Witten that where we have singularity, we should expect CFT. We are still on the way to identify the CFT, but maybe I am not so hopeful, but singularities will be resolved. It's expectation.
So you make the calculation taking the f of r equal to this exponential function with alpha, right?
Yes.
How difficult would it be to compute this trace that would give you the energy for a generic f of r? Because in that case, you can just phenomenologically, or not phenomenologically, but in a model building sense, you can try to constrain how the Schwarzschild function is the Schwarzschild function is modified, or which properties you should add.
It will be not easy to do for a generic f, okay? We did it specifically for this shape. No, I just want to specify it again so that there is some more context of your follow-up, okay? It is specifically to make all contributions of all equations, of all terms and equations of motion regular, Okay. So I don't know how to phrase this requirement in general. And technically, on the way of computing, you have to compute derivatives of this function in infinite number of times. I'm not sure what it will involve to make it generic. Okay. What we did, however, preliminary, we did it, but didn't include any in the paper, did it in different coordinate system and have shown that in Kerr-Schild coordinates, it does a great job either. So in principle, we can say that our statement is coordinate independent, or at least we have this hope, okay?
Well, I just wanted to test that I understood correctly. For a solar mass black hole, let's say, your solution will be exactly like Schwarzschild up to some up to a very close distance from the origin. I don't know, tiny Planck distance or perhaps a multiple.
Yes, you understood it correctly. Exactly.
So it's almost like GR.
Yes, we don't want to break everything what we know from GR. GR is great up to some extent, yeah. But we want to try to say something about theory at very high energy.
Can I ask you for? So is this a solution for you in your theory, or what is it?
No, it is not a solution. We don't know solution of vacuum equation. Neither I'm not sure how to say what is vacuum equation, because I don't know which part corresponds to geometry and which part corresponds to matter. Okay, but for this particular metric, for any given metric which you want to give me, I would be happy to have matter content which is at least physically, how to say it, viable. Okay, so physically it makes sense. Okay, what we could do for the moment, at least, to make mass of this object finite, or to put conditions such that mass of the object is finite.
And this does, if I do the same in GR.
If you do the same exactly computation in GR, exactly the same procedure, you will find out that integral from 0 to infinity of trace of equation of motion reveals you M. M is this M from Schwarzschild. It was done roughly 30 years ago by Balassin and someone else, I don't remember other author. From where they may...
What do I gain from your infinite derivative theory? What do I gain with respect to what I do in GR? Why do you do this in your theories? It's not a solution, you say, of those. It's not a solution in GR. Why should I?
You gain the fact that if you try to embed their Schwarzschild solution, you will have to Schwarzschild solution will correspond to infinite mass compact object. Okay? If compact at all. Yes, compact, but infinite mass. Schwarzschild solution in GR corresponds to finite mass object. Okay? And here it will correspond to infinite mass object.
In GR, and in infinite derivative is still fine. This is what you're claiming.
No, I'm saying that if I substitute Schwarzschild solution in GR equations of motion, it corresponds to a finite mass compact black hole. Okay? And in infinite derivative gravity, it will correspond to infinite mass object, which I don't know what. And so I should say that I would disregard such a solution from infinite derivative case.
Well, on the black hole topic. All right, so I have a question for Damiano on these purely vertical articles, which I found intriguing, but it's entirely new to me. How should I think about this? You mentioned sort of projecting out ghosts, and that seems like that's definitely an interesting thing to do. But is it a more general? Should I view it as a more generalization of quantum field theory?
Yes, there are several directions indeed. Indeed, it's more general because you don't need them to be ghosts. One thing. For example, a question that you may raise and came to me is the Higgs particle, are we sure that the Higgs particle is a particle from data? I don't think we can, it could be something like this, for example. And curiously enough, in this paper I mentioned by Pollini and Rocca, these Wheelerons, they also ask the same question when they introduced these Wheelerons. And it was many years ago, but so you don't have any need why the Higgs boson should be something, an entity like this. But the question is, okay, are there enough data or reasons to exclude this? There are enough data to exclude this for Z, W, many other particles, all the quarks. The point is that you see, we have never seen Z as we see the mu. We could, in principle, but that would take efforts that we cannot concretely realize. So I'm not sure if that answers your question, because there are various directions, and I would have to know what you are more familiar with to make this. But it is a general statement. So you could say quantum field theory is a quantum field theory of particles and purely virtual particles. And then you can say, okay, is this too much freedom? Not really, because when you introduce in a model like beyond standard model physics, you introduce a new thing. You could say, I can introduce new thing that is unobservable like these ones. Is that too much freedom? And I would say no, because actually we have a lot of freedom already in the standard model. We don't know why the content of particles is the one we have. You can add more. We don't know why the gauge group is the one you have instead of having more. And so that's one way of looking at it.
You can essentially add, for all fields, you can just add new fields which have these that are sort of tagged being purely virtual particles, and then they interact with sort of.
Exactly, they are like mediate.
You can just generalize and have two classes of fields.
Yeah.
One which is purely virtual and one which is ordinary fields. And the interaction strengths, is that the principle what I can do with this?
Yeah. Another way to say is think of an auxiliary field. It's a field that you integrate out algebraically and give it a kinetic term. These are like auxiliary fields with a kinetic term that don't come up into observable things. Or think about it in quantum mechanics. What would this be in quantum mechanics? I have not explored this direction, but I can share this with you in case somebody has ideas. It would be like an entity which has a wave function. So suppose think of the Meissner effect that expels magnetic field from some substance. And it's like having an entity which has a wave function that's expelled from detectors. That knows when you have a concentration of atoms that could detect it. Like you can see it's absurd, but think of the Pauli exclusion principle. It's like saying that an electron knows where all other electrons in his same state are in the universe and avoids them. So you have these funny effects in quantum mechanics. And indeed, you cannot talk about one electron. You have to talk about them, all of them collectively. So this is one way to think about it. Well,
this is a follow-up, well, sort of a follow-up question, as long as we're on to the first topic. So I missed, maybe understanding some of the basic motivation for introducing the purely virtual particles. So just a reminder, one way to think about quantum field theory is it's the solution to a problem, which is reconciling quantum mechanics, Poincare invariance, and locality. And there's sort of a folk theorem that if you try to do that, you land on quantum field theory. Of the standard form. And then if we want to compute physical things, they could be finite time correlators or the S matrix, but let's focus on the S matrix. If we try to do that perturbatively, there's a standard set of rules, which we all learn when we learn quantum field theory, and that, goes via, say, the Dyson's formula and the perturbative expansion. We end up with time-ordered correlators in the middle and a set of diagrammatic rules, etc. So there's that standard story. Now, what you're saying is sort of we start in the middle and we're just going to change the rules around. At least that's one way, I think, of stating what you were advocating in your talk. But it's not really clear what the deeper motivation is, or how to think of this. Why are we doing this in a sense? There are probably many ways in which we can change the rule around, but trying to understand what motivates this particular way of sort of tinkering with the rules, basically.
Yeah, actually, that's the relevant question. And well, first, one thing that I find in quantum field theory is that every time I start exploring some ideas, I always have to go back to the very first pages of textbooks in quantum field theory. I kind of start in the middle, really. And that's what you have to do it here. So basically, the idea is that I had was, let's go back to the basic rules and check whether we missed something, some possibility, something like that we could do, and with rushing in the good days of physics, because everything was driven by data, and maybe we had missed something. So the motivation of this is that rush, of course, led us to a long way of success with the standard model, but not gravity. There is an obstacle there. So then you can say, okay, let's continue from there, or let's go back. Every time I find, even trying to formulate quantum field theory in a finite interval of time, you have to go back from the basics. It's really not something I find it perturbatively, diagrammatically. I have to stress that this is what I want to do. Otherwise, formally, it's not.
Compute finite time, well, say correlators with finite time separations or things like that. You're saying somehow with a fundamental limit on
fundamental what?
Well, you're saying you want to focus on the finite time problem. And again, we can compute correlation functions where the separations in times are finite. Optical correlators, say not just the S matrix, but is there some more fundamental way in which you want to put in a finite time than that?
No, the reason was to extend the concept of purely virtual particles to finite time, because the original idea was, and normally it's too tight to the idea of S matrix, for example, the Leavik models and so on and so forth. So this was my own I thought that maybe this idea works only within the S matrix, and I would not be satisfied with that. So I went to finite time to see if it can be generalized. But as soon as I went to finite time, I had to go back to the very first pages of quantum textbooks in quantum field theory, because yes, you can say you can compute, but what do you mean you can compute in finite time? Because I don't see many computations around. My question was to do Feynman diagrams with that, perturbative Feynman diagrams, and not just being satisfied with the formal formula that tells me that you can in state e to the minus iht out state. That's fine. What is that diagrammatically? And can I do computations, and what happens inside diagrams as the usual analysis that you do for the S matrix, and then change what happens inside diagrams. Unfortunately, there is the possibility to do this extension even in that case.
So coming back to the original question, in the standard field theory context, we have sort of a progression where we start with some principles you want to reconcile, and then ultimately you end up calculating something via a well-defined set of rules. So you're sort of changing, or considering an alternative set of rules in the middle. And
from the beginning, what are the rules, for example?
so there's a question, is that coming from some deeper set of principles, or what principles are you modifying, or what is motivating this change of rules? And yeah, we don't understand quantum gravity, but is it directly addressing the central problems of quantum gravity? If that's the motivation.
The motivation is to go beyond the standard model, what we can do, and to reach what? Quantum gravity. So that was the motivation. That was my motivation, at least. I wouldn't have thought of this or anything like that if proceeding along the usual path had worked for quantum gravity. Actually, if you want to know the story, the story was completely different, because I was convinced, as I mentioned later, that quantum gravity is just Einstein gravity, no renormalizable, period. And I had interactions with some people who work on the subjects, as Alexei does, and non-local theories, and they mentioned to me Lee Wick, etc., etc. So I said, okay, Lee and Wick cannot work. Let's find a way to disprove Lee and Wick. That was my motivation. Okay, I wanted to disprove Lee and Wick because for me, quantum gravity is just Einstein gravity. Was Einstein gravity plus a cosmological constant. Period. It's not renormalizable. It's fine for thousands of years. We won't go beyond that. But then I gave a PhD thesis to a student, and every day I came up with a problem. Oh, I found a problem. Lee and Wick cannot work. And the next day I found a way out to that solution. And eventually that led to a different kind of models. So I started getting convinced that my own starting point was completely wrong. And now I have to admit that it was. Now you can ask, so this is a back and forth. I cannot say if you start from the middle. So the idea is to be as conservative as possible, change the minimum. And of course, in the end, you should not change, you should have agreement with data. So in principle, even giving up unitarity is okay. I mean, I don't want to put too much into the word principles, because people have proposed, and I cannot disprove them. I cannot disprove that a non-unitary theory is not good. I cannot prove that it is not good. For me, it is too much, but this is my personal. So basically, to go back to what I was never convinced was a strong principle in quantum field theory, was analyticity. That's it. Analyticity for me is a powerful tool, but not a principle. That brings together, when you break that, so you have to break it in a minimal way, the price that you pay, like this, let's say, causality, micro-causality. You do not have micro-causality. I do not want to use micro-causality or causality because I do not know what causality means. I'm serious on this. If this is a question to all of you. If any of you knows what a cause and an effect is, I would like to know, because I don't have a definition of that. I don't think that the notion of causality belongs to physics. So that is a principle I was completely happy with renouncing, because for me it doesn't mean anything. And I can, yes. So that is the principle that I gave up. Locality and let's say causality, the order of time, chronological order.
I think microcausality is widely viewed as a way of exactly formulating what we mean by locality and causality. So it's implied no propagation outside the light.
Yeah, but
that's a good starting point for quantum field theory. We may well need to go beyond quantum field theory to understand quantum gravity, and I think that's an important point. But at least if we're talking about quantum field theory, say, think about the algebraic formulation. That's one of the basic postulates. is, like.
Okay. So let's, I can answer to that, but let me also point out that this is dodging the question of what is causality first. I would like to know. In Toft and Veltman's diagram, there is a very nice comment on causality. And one is a definition that you can adopt of causality in quantum field theory is the Bogolyubov one, which is a certain identity for the S matrix, and that's fine. And another definition is a Kalman-Lehmann-Simansik-Zimmermann one, which is the commutators one. Both have a drawback. They are not dealing with physical quantities. One is dealing with operators, and the other, it's not my comment, it's Toft and Veltman, so I'm using the authority principle if you want. And the Bogolyubov one is also a problematic one because it is an off-shell. Well, now I'm thinking that off-shell is a good thing, but in a gauge theory, going off-shell without being cautious, you can you go to something that depends on the gauge fixing and so on and so forth. So anybody who thinks that causality is a strong principle, first I would like to know what causality is in a classical theory. And then we may talk about those, the strength of those definitions. But the criticism is those are not properties of on-shell physics, of observable quantities. You may have to do envision experiments, and many people tried. I'm not saying to you that I can go through all the proposals that have been done for experiments, testing this causality. To make it something concrete, you need an experiment, right? What would happen if causality were violated? What would you see? But my impression is that you can always turn these so-called experiments or proposals around to not see actually a true violation of what causality is, because you don't really know what causality is. So my first objection in a deterministic environment like classical physics is, okay, what is a cause and an effect? It's deterministic, so it's a one-to-one correspondence between past, present, and future. And for me, saying that past causes the future is the same as saying the future causes the past. I do not see it as any addition to what F equal ma is. This is an equation. You can endow it with all the talking you want, but there is nothing that brings a concept, adds anything in talking about a cause and an effect. So that's why I do not think that renouncing causality is a lot. But my challenge is, tell me what a cause is. And now when I talk to people, and I'm anticipating your answer is, okay, they downgrade the notion of causality to temporal chronological order, which is also not valid in microscopic physics in my theory. But that could be something. I don't know if this is clear, but probably not. Let's.
You can formulate microcausality as a principle. If you think about quantum field theory algebraically, it's the principle that observables commute, or the subalgebras of observables associated with space-like separated regions commute, and that's a pretty sharp proposal insofar as you can define quantum field theory in that framework. And the good features of causality come out of that. So for quantum field theory purposes, that seems to be a pretty good starting point.
Okay, so you can take that definition. I break it, so what?
Then you have to have a better alternative.
No, you have to tell me what's good in your proposal. It's just a proposal. It's just an identity for me. So what?
So starting postulate that is part of the
You're dodging the question. All data are compatible with that, and a small violation of that.
Yeah, super quick. Like, if you break that, can you make time machines? But I guess that's
So I don't know what you mean by time machine. Let me rephrase the usual objection I get from people, which is, okay, if you break, let's say, chronological order, you can go boost. You can go to a reference frame where this micro will become macro. It is like that. In my theory, it is like that. What's the problem? Is that if you take the maximum velocity of macroscopic objects in our entire observable universe, that's 1 divided by 300 times the velocity of light. So we never saw that. But in principle, it is. It is to one. It could be the star around the sun around, I don't know, center of the galaxy around. The maximum relative velocity is 1 divided by 300 times the velocity of light for macroscopic objects. And you would have to go to the velocity of particles at CERN, but still you would have to equip them with something to make an experiment. Try, it might be possible, but this is a prediction. Yes, you can travel back and forth in time within 10 to the minus 36 seconds. It doesn't mean anything because there is no time there, because there is no chronological order. So what does it mean to travel back and forth?
Exactly this question. You have commutators for space-like distances. It doesn't distinguish between past and future-like forms. This is a commutator for space-like distance. This is something clearly written in one of the top quantum mechanics paper, recent one, and also John recently one of the papers. So this commutator doesn't distinguish past and future. Maybe that will satisfy.
Yeah, but what I'm saying is that if in principle you can boost into like a macroscopic time machine, I'm just asking if this is the case. I mean, whether it's in principle.
In principle, you can do it.
That's all I want.
It's a prediction of the theory.
I have a follow-up on causality. In principle, we can define causality in a very physical way as the absence of resolvable time advances when signal is propagating on top of a background. And this is something which you can simply take your theory and compute.
The absence of?
Absence of resolvable time advance. What I call resolvable time advance is the one which is larger than allowed by uncertainty principle for particle of certain energy. So if the particle of energy omega is propagating on top of background, then it is allowed to have time advance 1 over omega. But if it's larger, then in principle you can arrange a time machine summing up time advances from these kind of propagations. But if it is less, then it becomes probabilistic, and quantum mechanically you cannot measure this kind of time advances. And causality defined this way actually consists well with Boголюбов causality, as in principle I participate in projects where I have shown this explicitly. So this thing can be applied to any theories like non-local theory or any other proposals for QFT. In principle, it's something you should just take your theory and compute.
So would you discard a theory that violates that principle? That's my question. Because you can accept the definition you want. Okay,
well,
fine.
That's more philosophical.
No, that's the relevant question because if you limit yourself to that as a restriction, we have many restrictions already in quantum field theory, and those restrictions are sufficiently powerful to reach a standard model, not to quantum gravity. So you have to give up something. My question is that I mean, I do not see that as a big price to pay, but that's a matter of taste.
As we have never seen that in the universe, I would maybe be more strict in causality, in the absence of macro causality or some micro causality, which can be summed up to macro causality. But if you can invent time machine, it would be also very nice.
So you're saying that if you violate your principle, I can accumulate effects and have it, but I can't do it practically.
Yeah. Then
so you can do you can prove that your principle is a principle of nature experimentally right now.
Yeah. Well, then you simply can check it.
But that's something you claim you can do now. It's done.
I don't know, it's done. It depends on the theory.
Yeah, well, there's a problem, and that is, in why we like causality. One reason is because if you violate it, and you have things like time machines, you can typically end up, or you typically do end up with inconsistencies, paradoxes, like the famous grandmother paradox. So,
The famous what?
grandmother paradox. If you're not familiar with it by that terminology, you're probably familiar with the concept. If I can send a signal back in time, I can create a paradox pretty easily. I can send a signal back in time to someone to kill my grandmother before my mother is born, and then a logically inconsistent situation. So, if you're going to find or consider some violations of causality, you need to at least figure out how to make them consistent with logic, right? And at least naive violations of causality, sending signals backwards in time. Well, even if you can send a signal backwards a little bit in time, then you can sort of imagine enhancing that effect by having multiple instances of sending a signal back in time and accumulate a large effect when you send a signal back in time, maybe with low probability. But even if you do that, you end up with logical inconsistency. So if we want to consider violations of causality, then we have to at least come up with some story about how we avoid inconsistency.
My story is that if you do that, that, as I said before, that's something you can do in principle. I do not claim that our universe is logic. I claim that what we have seen in 14 billion years and for 100 billion years from now will seem so. That's my claim. And within these may seem long amount of time, there is an appearance of logic. Yes. So what? An appearance of logic, like the one you claim. But so what? That's a matter of numbers. As I say, you can, in principle, do what you claim. It's just that if you put the numbers in, it's not something that is going to happen for billions of years. That's my claim.
I have this very small addition to that, but it's just that if you can make these CTCs like that, maybe that would if you couple it with unitarity, you get that the dynamics either you break unitarity or the dynamics is trivial because otherwise like the time evolution becomes trivial.
Yeah, no, more coffee break discussion.
I mean, what I'm saying is that you can do that. That happens within 10 to the minus 36 seconds. Okay, that happens all the time. It's happening here everywhere within 10 to the minus 36 seconds. Consider that we do not know what time is below 10 to the minus 18 seconds. So it is 18 orders of magnitude below.
It's not an invariant notion.
Yeah, and then if you want to boost, I have the other argument. There is no place in the entire observable universe that does that, has ever done that or will ever do that. Just check the energy you would spend to boost a macroscopic object to those velocities that you need.
In your reference frame.
In ours, yes, I understand.
Believing in Lorentz invariance is an issue.
No, I don't believe in beliefs. Sorry. I believe in data.
I was changing question for Alexis, which would be, you have the exponential wave entire function. And I'm having a hard time understanding how that would be preserved under loop diagrams. When you do loops, they're very complicated functions of the momentum. They have logs. If you do matter loops, matter loops combined with gravity loops, so you're going to bring in all the coupling constants and masses of all the particles in the world. How is that fact of an exponential of an entire function going to be preserved under quantum corrections?
It's a good question. First of all, I didn't say that we investigated how this is going to couple to matter and what will happen next. Yes, of course it has to be, yes. there are different ideas on the market about this, but if you even touch gravity, I agree with you that there will be a lot of things. But first of all, we worry about the possibility whether we need or not to renormalize all of this. Yeah.
About infinity.
You. Yeah.
Effects aren't, and, you know.
And by the way, we don't at the end of at the end of the day we don't disregard the logs. We expect some logs. Yeah, we need branch cuts and stuff like this to have how to say healthy theory branch cut to be arranged. It has to have some logarithm at the end of the day. Yeah, so in principle, as I told you, to everyone during the talk, it's not like a finished project. It's project based on some logical consequences from point 1 to point 2 to point 3. First, we write all the possible terms in the gravity action. Then we conclude. Then we single out the set of terms which can contribute to propagator, and then we find out the structure which will guarantee ghost-free background, ghost-free Minkowski background. Okay, and then we build up on this. And I agree with you that these are very impressively difficult open questions. How all of this will work in details. But if you don't write this structure, you either end up with ghosts, or you have to write something conceptually different, at least not purely algebra, not purely geometrical.
Want to add that in the example given by Alexei for scalar field theory, tree-level propagator exponent of logs becomes integral exponent instead, which has a log branch cut. So in principle, we expect of course there will be log corrections in finite parts of the action, and still it's another requirement to the original form factors to have log corrected effective form factors such that they don't bring new degrees of freedom.
Yes, actually, logs are not so bad because log. Yes, if you have a log in between of two scalar curvatures, limit is still Newtonian limit is still there. So log is okay. The only problem it's a bit more difficult to study it because there is no Taylor expansion and there is no technique which we usually do.
Yeah, good, thank you. Yeah, so you're addressing the singularity problem of black holes. But I think from a, well, somewhat of a more recent perspective in physics, you know, we've begun to regard the problems of black holes, or at least the deeper problem of black holes, as having to do more with the horizon in some sense. Namely, you know, the problem of unitarity in black hole formation and evaporation. That's really something that we've, I think, come up with fairly convincing arguments that, you know, just resolving the singularity doesn't solve that problem. Something new has to happen on horizon scale. So I'm wondering if there's anything else one can say in your approach, you know, with infinite derivatives that helps with that sort of other problem, the problem of basically unitarity for large, well, for initially large quantum black holes.
The short answer is not yet, but we are aware about the fact that it's very important direction to study. And because here it was, how to put it better, it was not our wish to remove singularity. It was our wish to study how at all one substitutes singular metric inside of infinite derivative equation. It was purely mathematical question because in if you just take Schwarzschild metric and compute scalar curvature on this before how say canceling different terms before bringing it to exact zero, you find out that it behaves like a delta function. Pure mathematical question would be how this distribution can be embedded in an infinite derivative equation. And then we found out that it cannot. And let's say resolution of singularity was kind of byproduct effect. Okay, our intention was to see whether what happens at all with singularity on the example of Schwarzschild, and how this can be combined with our understanding how propagator or shape of this form factor looks like. And what we found that either Schwarzschild and bad propagator, or good propagator and no singular Schwarzschild. And horizon and the other question which you raise, this is next step which we kind of on the way to address, but not immediately. I don't know good answer immediately.
Why do you believe this is a next step? I mean, just the standard arguments that the curvature scale, say at these astrophysical horizons that you find inside of the galaxy, say, the curvature is even weaker than in this room, right? So how would higher derivatives even be relevant for the generation of Hawking radiation near such a horizon? Well, what's the argument? How can I see it? I would say it's almost infinitely suppressed.
You are right, but the problem is that in our case we have to form an object which has two horizons, and usually presence of inner horizon will create even much greater problems than outer one. And then we may have some implications. I cannot say something definite now just because it was in the very initial stage of my thinking. But the main problem will arise not from the outer horizon, but rather of arranging two horizons, avoiding Hawking-Penrose theorems and stuff like this.
But the Hawking radiation is generated at the outer horizon, right? So
this is what I told you. I'm not sure that exactly explaining Hawking radiation or stuff like this will be exactly what will be next, but next will be definitely study of horizon structure and this how the metrics.
Yes, my question is probably totally related to what Alessia was asking during your talk. So you have this function f, and you have a lot of freedom. And the question is, does this freedom show up when you calculate some physical observable?
Yes, it somehow show up, and yes, it is a question how to narrow this freedom, how to single out at least some class of these functions. And all we know that we can, we did some job related to inflation and it already produced some restrictions, or better to say some ideas about this function for lower coefficients, and there should be several constraints which come from conceptual things like, for example, unitarity bounds, or for example, computation of amplitudes will give us, it's not done actually yet, it will give some constraints about shape of form factor and deep UV limit. And what happens in between, so I have no answer about it. Something joining analytically, some at low and high energies.
At the end of the day, the normalizability of your theory will be the stronger one, a stronger way to fix the coefficients of your form factors. Because if you study the flow for the entire form factor, then you can exactly fix the coefficients of the fixed point, and via standard techniques then derive the effective direction that will fix infinitely many of those coefficients as a function of hopefully few relevant
Yes, I totally agree. The only obstacle on the way whether we'll be able to compute this running, but I hopeful because we have now very great workforce, because we have as a postdoc in my group Oleg Melichev, who was a PhD student of Roberta. So I have some hopes that we can do it, but it already have taken 1 year, you know, and it will take a bit more.
Coming back to your
singularity resolution and the computation. I was wondering, once you insert the Schwarzschild into this integral, whether you have to take care of boundary terms and whether you can do partial integrations, because some functions don't fall off enough so that boundary terms would not contribute. And then if this is the case, you would have to include more terms in your action because box R cannot be transformed into R box squared on.
Yes, we blindly assume that boundary terms don't contribute. Otherwise, you will end up with infinite number of boundary terms, and it will be not that action for sure. Yes, we hope that they don't contribute.
I have a quick follow-up question, Benjamin's. So, well, basically taking the Meissner's point of view, if you have quantum gravity, quantum nature automatically removes the concept of singularities, which are classically, to put in the context of Damiano, for example, he presented some way to have UV complete quadratic gravity as Schwarzschild singularity. If the quadratic gravity is full theory of quantum gravity, of course, modular prescriptions all work, then singularity is not a problem because it's automatically avoided. So why do we care about solutions without singularity if we have quantum gravity?
As I told you, we didn't care about whether there is singularity or no. We found out that singularity is not compatible with a well-behaving propagator.
In your theory, but
Yes.
In general about singularities, if we have quantum gravity, singularity is not an issue.
If you have quantum gravity, yes, I have no yet, so I worry about them so far.
Can you then define the word singularity?
We cannot define it. I mean, if we have quantum gravity, we have at short distances, some uncertainty will kicks in, whatever the uncertainty you maybe depending on what kind of quantum gravity.
But singularity in the end means that something is infinite and cannot be calculated. So if you have a quantum gravity, everything should be calculable and finite. So in that sense, there's never a singularity in a proper quantum gravity theory.
I guess you meant the word self-consistent manner as well. You just assume, start from a set of assumptions and check if they are consistent. It can still be that you have a theory of quantum proposal, but if you have quantum gravity, which is unitary normalizable, but there's other problems like a singularity resolution, and then you have to rule it out because there are other conditions.
Okay. And then you may have singularities in, for example, you don't care about singularities in PVD, so because at some point, at some distance scales, quantum electrodynamics kicks in, but then it will, you do not worry about singularities in electrodynamics. So in the same way, if you have singularities, coordinate singularities.
I mean, it is valid up to some large scales,
But again, the question is, what is the problem if you have a solution with singularity? Realistically, it will never be a singularity.
That's the question. So, just because you have a solution with singularity, that at Planck scale, quantum effects of gravity kicks in, so then you cannot quantum mechanics.
No, but once again.
Actually equal to zero, so then you do not have singularity. So
no, but once again, if it was a question to me, I told you it was not our intention to prove or disprove presence of singularities. It just was try to see what happens to well-known solution of GR. GR has Schwarzschild metric as a solution. Okay. So it was just a try to see what happens to such geometry if you substitute it inside of other equations of motion. And we have found very simple correspondence between necessity of propagator to grow properly and ability to substitute this solution without pathologies. By product, we found, for example, that R-squared gravity is totally insensible to this. We can substitute this contribution to total energy doesn't appear from quadratic gravity, and it's like R-squared, and it's fine. You can substitute there whatever. As well as presence of singularity in geometry doesn't mean that you have a singularity in physics. Yes? The latest paper by Kerr was exactly claiming that even though you have singularity in a Kerr black hole, it doesn't mean that geodesics definitely hit the singularity. Fine, you have singularity in your geometry, but if you can never reach it, then what's the problem about this? So that's a bit more, let's say, philosophical question what you want to from this notion of singularity, but it was not our intention to remove them or support them. It was our intention to see what happens to a well-defined solution which should describe something like a compact object. Okay, because any compact object like a star behaves like a Schwarzschild at large distance. Okay, so we wanted to see what happens in our new description. We want stars to exhibit the same Newtonian potential at the end of the day.
Still related to the codes in your case. And instead of basically what you're doing mathematically, just saying, okay, take this Schwarzschild method, I plug the method and we prove it in the equation and try to see whether this solve or not the equation with some sensible, for instance, finance contribution. And you notice that there is some which easily needs some infinite makes sense. Yes, but we already discussed this about make this comment again. In GR, the vacuum is not a solution type of zero, just a vacuum solution, which means that if you have a star or it is, the vacuum will be the solution outside the object, so a vacuum solution. Today, just as some solution. And even here, if you just say I have something and I want to check whether it's actually the vacuum solution, which means H equal to 0, it will be a solution. For instance, in some of the cases where you have that vial, for instance, you understand it can solve the equation Z equal to 0. So, I mean, the question I ask is really interesting because we are trying to just understand what happens if you include the point I and 0. But in my opinion, to make the question more feasible, you should really study what happens in a dynamical process to really say whether or not it actually will be a solution that you can work. Because in Schwarzschild, I equal to 0 is not, I mean, the singularity is not really a time-like point, it's a space-like region.
Sure. This is why we have taken regularized Schwarzschild, because if your process is somehow adiabatic, which means going slow, it means at any stage before it collapses to whatever we know in GR, it should be some regular metric everywhere. So somehow regularization can resemble you some moment of collapse, if you want. Intrinsically, you want me to do something what people didn't do even in GR, construct systematically collapse of matter.
Inside some shell, outside the
No, I don't object. It's a great problem, even in GR. And here it's even greater, infinite number of times, because I have infinite number of derivatives. Yeah. But you are right, it would be incredible to do it. I have no idea how to approach it, even where to start.
The generalization of the Oppenheimer-Schneider collapse in space. Of course, you need junction condition in this case, which will be much more complicated.
They will be impossible because you have to junction condition in GR involve two derivatives, and here there are infinitely many. It is not like a trivial task to do.
Yeah,
I don't say it's impossible, but it's something way more complicated.
Question really ask physically whether or not you form a singularity.
Sure. I would be happy to address it. Maybe you can guide me how to do it. But it's complicated, you know.
Wonderful thing, wasn't it? I just wanted to ask you to clarify what is the role of the integral action. So I did not get exactly if that is your Bayer action or what is its role, or and if it is not your Bayer action, what is your Bayer action?
So think of take a 4-fermion vertex, for example, like in the weak interactions of Fermi, the first, and you pop it up into by inserting a particle. So let me maybe write if there is. So if you have a 4-Fermi vertex, you can introduce a scalar field and write it this way, right? Well, if you do it this way, this starts propagating. So it's like some intermediate thing. Now, this is an auxiliary field so far. And if it gets dynamical, it becomes a particle. So if it is treated the way I say, it's like the difference between the classical action, which will have a dynamic part, and what I call the interim action. And the true physical one is that the physical one, this extra field is like an auxiliary field. So it is not in the external states. And so the true classical action is the one which considers only the 3 diagrams with the psi's outside and sigmas inside. But if you want to ask about the Bayer action, it can be either of the two, because in quantum field theory, it's better to work in a local framework and put renormalization constants everywhere. That's very convenient. But once you integrate something out, no matter what prescription you use, because these prescriptions do not change the ultraviolet, so the renormalization will always be the same. Those simplify in between vertices and diagrams. So you could also work with a Bayer action in a local form. That's not good to compute the diagrammatics that I will give you, because you will have to go back. You cannot use this as a propagator inside bigger diagrams. But the difference between interim and non and physical is the same difference as you would do in gauge theory, where you do need to implement, so insert a Faddeev-Popov determinant, and you don't do it in a Faddeev-Popov as a determinant but you modify this, right? So you have an interim classical action in gauge theories as well, that you normally call the gauge fixed action. It's not a classical action, the true classical action. You don't think that there are ghosts of this type, you just use it. But for randomization purposes, a Bayer one, it can be either way, this one or the one where you remove. It's difficult to work with a gauge fixed action, but it can be done in principle, and people did it. You can resolve, you can use the axial gauge. Frequently, they use the axial gauge to remove the ghosts. Instead of d mu a mu, they use a vector and n times a. But in principle, you can do renormalization even in the complicated form. So it's just a difference between the tool you use to keep everything local and the physics that is the one you test. Yeah, you could use both. Yes. It's like an auxiliary field. So you can add it, remove it. You use it just to keep things simple from.
Okay, we will continue our logical questions, whether classical or quantum logic, after lunch. Let's thank Alexei and Damiano.